Okay, well, hello everyone. Welcome to the probability seminar. Once again, we're very glad today, very happy today to have Fabrice Baudoin from UConn visiting. So a little bit of a background about Fabrice. He's originally from France. He got his PhD from University Paris 7 in 2002 and has had several positions since then. He was at Paul Sabatier University. He's been at Purdue for a number of years, and now since 2016, he's been a full professor at UConn. He's been working his specialty, his area of expertise. Looking at his papers, it looks to me like his area of expertise is stochastic analysis, also differential geometry. He seems to have written a lot of papers sort of in the combination of those two fields. He's written many papers, nearly 100 papers, many highly cited papers and so forth. And we're very happy to have him today. He'll be talking to us today about the Brownian windings, random matrices, and hyperbolic Stiefel fibrations. Please go right ahead, Fabrice.
Yes, okay. Thank you very much, Greg, first for giving me the opportunity to give the talk, and also thank you for the introduction. So today, indeed, I'm going to speak about a topic which is at the intersection of probability theory and stochastic calculus with differential geometry. So this is a topic I have been interested in for several years, which is a study of Brownian windings in different geometric settings. So today I will try to explain the connection between Brownian motion, random matrices, and Stiefel fibrations. So let me start with some basic motivation for the problem I will be interested in, which is a description of the winding for the Brownian motion in the plane. So consider in the plane from which you remove 0, the one form x dy minus y dx over x squared plus y squared. So this form, it's natural to call it the winding form of the plane because any smooth path can be decomposed into a radial part and angular part. That is, if you take any smooth path from 0 to plus infinity, which takes values in c minus 0, you can always write gamma as a product of this modulus of gamma t, times exponential of I theta t, where theta t is going to be angular motion that we can compute explicitly as a line integral along gamma. That is, if you integrate the one form x dy minus y dx over x squared plus y squared along the path gamma, what you get is the angular motion of the path. So with this in mind, this is natural to call alpha the winding form around 0 for the path, since it quantifies the angular motion. So as a probabilist, we are interested in Brownian motion. So you had a small movie about Brownian motion. As you could see, it describes a winding motion around 0. So the problem people have been interested in for quite a long time, this is to study the winding of the Brownian motion. That is, you take a random curve in the plane and you try to see how fast does it wind around 0. Are you able to compute winding numbers? Are you able to obtain asymptotic laws or problem like this? So mathematically, the problem is posed as follows. So you consider a two-dimensional Brownian motion that I write in a complex form for convenience. So you write zt as xt plus I yt. So we assume that this is not started from 0, so that we can make sense of the winding of z around 0. And it's actually possible to give a meaning of the integral of the winding form alpha along the path of the two-dimensional Brownian motion. It's possible, but this is not trivial, because if you have in mind the picture of the Brownian motion, which is here, this Brownian motion is nowhere differentiable. That is, you have a motion which is nowhere differentiable. So the integral of alpha along the path of z has to be defined in some special sense. This is not defined in the usual calculus sense, simply because the paths of z are nowhere differentiable. However, nowadays, this type of object that is integrating one-forms against non-smooth paths is well understood. We can either use Ito calculus, which is a series from the 1940s, 1950s, to give a sense to the integral of alpha along Z, or you can use a more recent theory of rough paths that says that actually pathwise you can make sense of the integral of alpha along Z. So we have a process, zeta t, that evolves in time, which is given as a random variable. It's a stochastic process depending on t. It's given as a Ito integral. That is, this is an integral constructed using Ito calculus. And one of the basic problems is to study the distribution of zeta t, which is called the winding process of the two-dimensional Brownian motion. So there is a beautiful old result, which is due to Spitzer in 1958. He proves the following limit in distribution for the winding of the two-dimensional Brownian motion. So zeta t multiplied by 2 over log t converges in distribution to a Cauchy distribution with parameter 1. So this implies in particular, due to the factor log t, this implies that you have infinitely many windings around 0. That is, if you start a Brownian motion, you leave it, you keep it running forever, the process will wind infinitely many times around 0 with a rate log t, essentially. And there is an exact asymptotic law that describes the winding motion. So there exist many proofs of Spitzer's theorem. So there is the original proof due to Spitzer. It's a proof which is based on PD. Spitzer used Feynman-Clark representation for solution of PDEs and solved explicitly a PDE. There is a proof which is due to Marker, which is a proof which is possible to generalize in the geometric setting I will be describing today. So in the last few years, I've been interested in analogs of Spitzer's theorem in geometric setting. What does it mean? It means I had been looking at Brownian motion on manifolds, Brownian motion on surfaces, and I try to understand how does this Brownian motion wind in the manifold. So I will first present some few results in settings which are easier to understand. The first one being the Brownian motion on the sphere. That is, I gave you a small movie, about Brownian motion in the plane. But as you can imagine, it's possible to construct Brownian motion on a sphere. That is, you can describe random motion on a sphere, and you have a Brownian motion as a diffusion process associated with a Laplacian on the sphere. So it's possible to study and construct Brownian motion on the sphere. So with my collaborator Wang, we proved in 2017 the following results that describes the winding for the Brownian motion on the odd dimensional sphere, where we see the sphere of odd dimension as being embedded inside of Cn. This is why we consider spheres of odd dimension, so that we have an embedding inside of C to the n, which allows to consider the polar decomposition of the components of that Brownian motion. So if you look at the Brownian motion on the 2n plus 1 dimensional, 2n minus 1 dimensional sphere, its components are complex numbers because the sphere is embedded inside of C to the n. And I'm looking at the polar decomposition of the first component. So I'm choosing here the first component arbitrarily, meaning that I could choose the second one, the third one, or the last one, it will not change the result. So we have the polar decomposition into a motion exponential of I theta 1t, which is the angular motion, and we have a modulus of z1 for the radial part of z1. So theta 1, it makes sense to call it the winding of the Brownian motion path around the north pole of the sphere. And for this winding, we prove the following limit in distribution, that θ1 over t is going to converge in distribution to a Cauchy distribution again, but this one with parameter n-1. So I just realized that there is a typo in my slide. Cn-1 is a Cauchy distribution with parameter n-1. So you might observe that, therefore, there are also infinitely many windings. That is, the Brownian motion on the sphere will wind infinitely many times around the North Pole. However, it winds faster. That is, the rate at which it winds around a fixed point is t, and not log t as it was in the complex plane. Well, we can understand this intuitively from the fact that the sphere is compact, so you have less space for the Brownian motion to move in, so it has to wind more because there is less room for the Brownian motion to move in. So I'm going to say a few words about the proof because the proof is interesting. The proof will consist of two parts. In the first part, we'll have to compute the winding form. So I try to explain you that in the plane, there is the one form that plays a special role, this form x dy minus y dx over x squared plus y squared. Well, we need to try to find an analog of that form on the sphere. So to construct that form, we use complex geometry. That is, it's useful to see the 2n minus 1 dimensional sphere as being a bundle, more precisely a circle bundle over the complex projective space Cpn minus 1. That is, there is a well-known fibration, which is called the Hopf fibration, that says that the sphere 2s2n minus 1 is a circle bundle over Cpn minus 1. So these winding form that we can compute on s2n minus 1 is constructed from a form eta on the complex projective space whose exterior derivative is the Keller form of Cpn. That is, it's interesting to relate the angular motion on the sphere to the Keller form on Cpn minus 1. So once we have this connection, that is how the angular motion on the sphere is related to the motion on Cpn minus 1, we have a formula for the form eta. And once we have this formula, we can use techniques from probability theory to compute explicitly the characteristic function of the winding process. So it's worth noting that not only do we get an asymptotic result, that is that θ1 over t converges in distribution to a Cauchy distribution with parameter n-1, we actually also get a formula, which is a complicated formula, but this is kind of explicit formula for the characteristic function of θ1. So here we can summarize the situation by saying that in some sense, the geometry of the Hopf fibration is the one that controls the Brownian windings on the sphere, and the winding form of the sphere comes from the Keller form on the space Cpn minus 1. So this is the first geometric setting in which we have been able to prove explicit winding result. We have been then interested in a natural generalization of spheres, which is a unitary group. That is, we have been trying to understand first the Brownian motion in the space of unitary matrices, and then try to understand what is winding in that setting. That is, if you have a path in the unitary group, what does it mean that this path has some winding? So consider the unitary group UN, which is a set of n by n complex matrices, such that m star m is equal to identity. So this is a space of the space of unitary matrices. They preserves the Hermitian standard Hermitian structure on Cn. So this is a compactly group of matrices. This is one of the classical simple Lie group of Élie Cartan theory. So it's possible to construct Brownian motion on this unitary group on UN by solving a stochastic differential equation. So the equation is very simple, and this is just a linear equation. So essentially, you take a Brownian motion on the Lie algebra of UN, which is known to be the space of Q Hermitian matrices, and you solve the stochastic differential equation. dut is ut times dbt. So this is really an equation that takes values in set of matrices. So if you like concrete things, this is really a set of equations that is, you can write all the entries of the matrix ut and write an equation for the entries of the matrix ut. So you are just dealing with a linear equation in a matrix Lie group. So this is a way to construct a Brownian motion. So it's natural to construct, let me say that it's natural to call U this Brownian motion on the unitary group because you get a process which has stationary and independent increment. This is therefore a natural generalization of the Brownian motion on Cn. So in that context, we prove the following theorem. Look at the Brownian motion ut. So ut is a matrix, right? So this is a matrix with n by n entries, which are complex entries. So I can look at the block decomposition of ut. So you will have several blocks. I denote them by x, y, z, and w. And I take z to have size k by k. So that the bottom left corner of the matrix ut has size k by k, and n is the total size of the matrix. So we can look at the determinant of zt, because z is a square matrix. So for instance, if k is equal to 1, determinant of zt is just the entry itself. That is, if k is equal to 1, zt is one of the entries of ut. This is the bottom left entry. So determinant of zt is a complex number, so therefore you have a polar decomposition. It decomposes into a radial part, rho t, an angular part, exponential of I theta t. So I'm going to call this theta t the winding, of the process determinant of zt. So for instance, when k is equal to 1, we just have the polar decomposition of one of the entries of the matrix. And by the way, here I choose the bottom left corner, z, but I could choose actually any minor instead of the matrix, okay? That is the theorem I'm dealing with. They are invariant, under permutation of the coordinates of the entries. So the theorem we proved is that, again, we have an asymptotic laws when t goes to infinity, theta t over t converges again to a Cauchy distribution, but this one with parameter k times n minus k. So it's interesting to see the index of the Cauchy distribution, which is related to a geometric quantity, k times n minus k, which turns out to be the rank of a symmetric space, which controls the geometry of the problem. So let me point out that this theorem of the unitary group is an extension of the theorem on the sphere. Indeed, it's not too difficult to see that if you take a unitary Brownian motion, then its first column is a Brownian motion on a sphere. So with this in mind, determinant of zt, when k is equal to 1, this is one of the entries of a Brownian motion on the sphere. So when k is equal to 1, we recover the previous theorem. So the proof is again split in two parts. You first have a geometric part where we try to compute the winding form. So the winding form of the unitary group these times will come from a Kähler structure on an underlying symmetric space, which is a complex Grassmannian space. So we can construct the winding form on the unitary groups. That is, we can get a formula for theta, which is the angular motion of my minor in the unitary group, in terms of the one form on the complex Grassmannian, with exterior derivative is the Keller form of the Grassmannian space. So there is kind of a similar structure, that is, the D group UN can be seen as a bundle over the complex Grassmannian space. I will explain a little bit more this construction a little later in the talk. But this is a construction that naturally generalizes the Hopf fibration. So this is for the geometric part. For the probabilistic part, we use stochastic calculus and random metric theory. That is, once we have a formula for the form eta, and for the winding form, we want to compute the distribution of a stochastic integral, that is a distribution of a random variable, and we are able to use stochastic calculus to compute this distribution. So in that case, as I told you, what plays the role of the Hopf fibration, this is the so-called Stiefel fibration, which realize un over un minus k, which is a set of k-frame in Cn. This is an homogeneous space. It realizes this space as a UK bundle over the complex Grassmannian, un over un minus k times uk. And as before, you know, the windings motion are controlled by the Keller form on the complex Grassmannian. So this is a situation for compact situation. We studied other compact settings like quaternionic Hopf fibrations. But in this talk today, I would like to present a non-compact situation which is negatively curved. I show you to start with winding, you know, in the plane, which is flat. So we have a rate of divergence in log t. I show you windings in compact complex spaces where we have typically a rate of divergence in t and a limiting law, which is Cauchy. Now I want to explain in a little bit more details a non-compact situation which is negatively curved. This is an extension of the complex hyperbolic space. So consider the following hyperbolic Stiefel fibration that I'm going to try to explain what is this set and why it is interesting for us. So the hyperbolic Stiefel fibration starts from a group which is not the unitary group anymore because it's going to be a non-compact Lie group. This is a Lie group un minus kk. So this is a set of n by n matrices. That is a set of invertible matrices n by n, which preserves the following form, Hermitian form, with signature n minus kk. That is, this is not the standard Hermitian structure on Cn because this is not positive definite. You have a signature n minus kk. So the group of matrices which preserves, you know, this pseudo Hermitian structure is non-compact because the unit sphere, you know, for the pseudo Hermitian structure is non-compact. So we have a Lie group of matrices. This is a group of matrices. And we consider inside of this Lie group the set of columns. First k columns. That is any matrix M, which is in the Lie group un minus kk, is a n by n matrix. And if you truncate this matrix, that is, if you look at the first k column, you are going to get the space HVNK, which is a set of first k columns of a matrix which is in un minus kk. So it can be described algebraically, that is, if you check that xz is indeed the first k column of a matrix in un minus kk, you should have that x star x minus z star z is negative ak. So this is a non-compact complex space. This is algebraic. This is a submanifold of C and K. It's possible to see that the dimension is 2nk minus k squared. Also, it's possible to see that as a set, as a Riemannian manifold, HVNK turns out to be homogeneous, turns out to be a coset of the space un minus k by the subgroup un minus k. Indeed, this comes simply from the action of the subgroup un minus k on un minus kk, where you just do a permutation, you just do a orthonormal transformation of the first k columns. So from this space HVNK, which is called the hyperbolic Stiefel manifold, we can take another quotient, that is, this is possible to have UK act on HVNK simply by right multiplication. That is, if you multiply a matrix in HVNK on the right by a matrix of UK, you have another element in HVNK. This is easy to see, for instance, from the equation x star x minus z star z is equal to negative ik. So the quotient of HVNK by this action, UK, it's called the complex hyperbolic Grassmannian. So this is a symmetric space. So this is one of the classical symmetric spaces in Cartan list. And this is a very interesting one because this is a complex symmetric space. So not only is it a Riemannian symmetric space, but this is also Keller. That is, it admits a complex structure which is compatible with the Riemannian structure of HGNK. So the rank of that space is K, and this is a space which is not compact. So for example, if K is equal to 1, this complex hyperbolic Grassmannian turns out to be the complex hyperbolic space. So we have a fibration of spaces. That is, we have the hyperbolic Stiefel fibration. UK acts on it, and the quotient space is HGNK. This gives a fibration, and the natural projection map from HVNK to HGNK turns out to be a Riemannian submersion with totally geodesic fibers, which are isomorphic to UK. So this fibration is called the Stiefel fibration. So this is a non-compact analog of the fibration that I described in the Hopf case. That is a Hopf fibration, or the fibration for the Grassmannian space. So this is a geometric setup. We have this Lie group un minus kk, which preserves my pseudo-Hermitian matrix. We have the hyperbolic Stiefel manifold, which is a set of first k columns. And then we have a quotient space of the set of k columns by the group UK, which is the hyperbolic complex Grassmannian. Let us study Brownian motion on those spaces. So I will start to study Brownian motion on the complex Grassmannian space, because this is the one which, in a sense, is the easiest to study. And this is the one that controls the geometry of the winding in the Lie group un minus kk. So one basic theorem is the following. Consider a Brownian motion on the Lie group un minus kk. So this Brownian motion can be constructed exactly as a Brownian motion in the unitary group. That is, you just need to solve a linear equation. You know, the object I am dealing with, even if they are constructed in sophisticated geometric setting, after all, they have a very concrete description as solutions, you know, of matrix stochastic differential equations. So consider a Brownian motion on this Lie group un minus kk. I have a block decomposition y, w, x, z. So I look at the last k columns. So this time, instead of taking the first k column, I take the last k column. This is purely for notational simplicity in one of the theorems that I will be stating later. So consider the last k column, xz. So the claim is that you get a Brownian motion on the hyperbolic Stiefel space. That is cutting the matrix U, taking the last k columns, give you a Brownian motion on HV and K. And moreover, we can describe the Brownian motion on the hyperbolic Grassmannian as xz minus 1. So this means that xz minus 1 is a representative, in the coset of the hyperbolic Stiefel manifold HVNK over UK. And this representative describes a Brownian motion when x and z are the last columns of the Brownian motion on UN minus kk. So we have a Brownian motion, W, that can be written in terms of the Brownian motion Miley group. W has size n times k. So if we look at W star W, this is a process which has size k by k. This is a Hermitian matrix. That is, if W is a matrix, W star W is obviously self-adjoint. That is, this is a self-adjoint matrix. Therefore, it has eigenvalues, real eigenvalues, lambda 1 up to lambda k. Let me denote these eigenvalues by lambda 1 up to lambda k. So what we proved is that there is a rational transformation of the lambda I, 1 plus lambda I divided by 1 minus lambda I, so that we get a process which can be described in terms of special diffusions, which are called the hyperbolic Jacobi diffusions. So more precisely, the theorem is that 1 plus lambda divided by 1 minus lambda turns out to be equal in distribution to a collection of independent Jacobi processes, which generator is given in the right formula, which are conditioned never to collide. So what does it mean? It means that you have a very well-defined one-dimensional generator, in red, in my slides. You start k diffusions independently with this same generator. So they don't start at the same point. You start them independently and you condition them never to collide in the dupe sense. You get a new Markov process. This is a result by Carling and McGregor. And you get a new Markov process which describes, this 1 plus lambda over 1 minus lambda. So in particular, from this description, we are able to compute, or at least to get a formula, which is kind of complicated, but this is still a formula. We get a formula for the distribution of the eigenvalues. So not only do we get a formula for distribution of the eigenvalues, but we are also able to compute, and this is very exciting result. So it does not look like it is in the slide because the formula is very complicated. But this is exciting because not only are we able to compute the distribution of the eigenvalue at a time t, which follows from standard theory about Markov processes due to Carling and McGregor, but we are also able to compute some additive functional, namely the integral from 0 to t of the trace of J, which is therefore integral from 0 to t of the sum of the eigenvalues. So we have a formula for the Laplace transform of this functional. So why is it exciting? Because there are very few functionals of Brownian motion for which you can have an explicit formula for the distribution. That is, in general, when you are dealing with random variable, processes, fields, very often you are not able to compute explicitly the distribution of the fields you are dealing with. So each time you get a new distribution from which you can compute the distribution, you are very happy because such distributions, such functionals are called integrable functionals, and there are very few of them. So this integral from 0 to t of the trace of J is an integrable functional of a Brownian motion on this complicated space. So this is a formula in terms of a determinant. So this is a determinantal process. And the proof is very long. That is, the proof of this formula is very long. It uses a sophisticated version of Gersonov theorem, which is due to Marker. So while the proof of the distribution of the eigenvalues is okay, that is, it uses standard tools, this computation is much more involved. In particular, once we have the exact distribution for the integral of 0 to t of the trace, we get a very nice asymptotic theorem that there is some kind of beautiful and magical cancelling in this ugly formula. That is, you have a formula which is very complicated, right? With some constants that I did not write, but we can explicitly compute them. And everything simplifies at the limit, and we get this very nice result that when t goes to infinity, 1 over t integral from 0 to t of the trace of J goes almost surely to K. So this gives a rather complete, not complete, but that gives a rather good understanding of the Brownian motion on the complex Grassmannian. We understand very well its eigenvalues, and we have formulas, for a functional of the trace. Let's go for the Brownian motion in the hyperbolic Stiefel manifold, which is obtained by lifting the Brownian motion on the hyperbolic Grassmannian. So try to keep in mind these fibrations that I told you about a few minutes ago. We can see the hyperbolic Stiefel manifold as a UK bundle over the hyperbolic Grassmannian GNK. And in particular, I pointed out that you have a remanent submersion from HVNK to HGNK. And this remanent submersion has totally geodesic fibers. So from general theory of Brownian motion on manifold, we are then able to represent the Brownian motion on the top space of the fibration as a skew product. So intuitively, the situation is that if you have a motion in the middle space of the fibration, this motion will have components in the spaces UK and the spaces H, G, and K. So this is kind of a far-reaching polar decomposition. That is, this is an extension of the polar decomposition, where Brownian motion is decomposed into two parts, a UK part and a HV and K part. So this polar decomposition can be expressed as follows. Consider a Brownian motion on H, G, and K. Solve the following differential equation. d theta is dA times theta, where A is the integral of a one form, which turns out to be connected to the connection form of the fibration, of the Stiefel fibration. So more precisely, this is a push forward of that form. And this is a form on HGNK whose exterior derivative turns out to be the Keller form of HGNK. So this theta is the analog of the exponential I theta t, where theta t was, in the complex plane, the integral of the one form. So here the situation is much more complicated because my process theta lives in the UK group. That is, this is a space of unitary matrices, and my form eta takes values in the Lie algebra of UK. But this is kind of the same idea. Cis theta t describes the angular motion of my Brownian motion in HVNK. And what I'm doing here is really a polar decomposition. So the polar decomposition explicitly write as follows. Your process W as a process which is given by this formula, that is WTIK times IK minus W star W to the power negative half times theta T. This one turns out to be an horizontal lift of the Brownian motion of my hyperbolic Grassmannian to the hyperbolic Stiefel space. This is due to the fact, essentially, that the submersion has totally geodesic fibers. Moreover, you can describe the Brownian motion on HV and K in terms of this horizontal lift. So if you multiply tilde W by omega T, where omega is an independent Brownian motion on UK, you get the Brownian motion on the hyperbolic Stiefel space. So this is where things are very nice, because I told you that there was a formula we liked a lot. This is a formula for the trace of J. And it turns out that the integral of my one form, trace of eta, can be expressed as a Brownian motion, which is time changed with a trace of J. So I was able in a previous theorem to compute the distribution of the integral from 0 to t of the trace of J. So C is representation of the trace of eta, that is the integral of the trace of eta along W, allows me to have a formula now for the integral of this one form, that is from the formula for the integral from 0 to t of the trace of J, I get a formula for the integral of the trace eta over the path W. So this allows to conclude the following. Let's come back to the starting point. You look at a Brownian motion on the Lie group UN minus KK. So you have a block decomposition YX WZ. Look at Z, which is the right bottom corner. Assume that this is a K by K matrix. So determinant of Z is well defined, because you look at the determinant of a K by K matrix. This is a complex number. This complex number can be decomposed into radial part, rho t, and angular part, exponential of I of theta t. It turns out that this theta t has a formula in terms of this integral of the trace of eta along the path of W. That is, trace of eta is a winding form on my Lie group, UN minus KK. So what is the limit theorem in that case? So we are in a hyperbolic situation. The spaces are negatively curved. My theta t still is going to go to infinity. That is, I'm still going to have infinitely many windings, for the determinant of ZT. But this time it winds slower. That is, we have a decay rate of square root of t. And we don't have the Cauchy distribution anymore at the limits. We have a normal distribution. So this is the central limit type theorem for the winding in hyperbolic spaces. So the situation in hyperbolic situation is quite different from the situation in the compact cases, which are positively curved. We don't have the Cauchy distribution anymore. So I tried to give you several examples, but maybe at this point, you understood that there is kind of a general theory behind everything. That is the Spitzer theorem that I presented to you today, the first one in the complex plane, which is the simplest one. The one on the sphere, the one on the unitary group, the one on the space UN minus KK. They are all part of a class of spaces on which we are able to compute those winding functions. So let me describe a little bit this bigger picture in which we have been doing this work of understanding winding. So this is a research program concerns the study of integrable functional. So what is an integrable function? Consider a Riemannian manifold M. On it, we can construct a Brownian motion. That is, we can construct a Brownian motion on any Riemannian manifold. Consider on that manifold one form, which takes values in some Lie algebra. That is, you take some Lie algebra valued one form, and you can compute the line integral. That is, you can compute the integral of alpha along the Brownian motion path. You get a random variable, that is, you get a stochastic process, which takes values in a Lie algebra. And we call this functional integrable if the Laplace transform can be expressed in terms of special function. So what do I mean by special function? So here, this is a terminology which is rather vague, but these are functions which belongs, to the class of hypergeometric functions, associated with symmetric spaces. So essentially, the functional is integrable if I have a formula for the Laplace transform. There are very few integrable functional. That is, I gave you the winding functional in the plane. There is another one that you might know. It's a Levy area formula. That is, the Levy area of the Brownian motion is also integrable. That is, we can compute its Laplace transform. And to construct a lot of them, we generalize, the construction that I presented today. Let me give you the following rough recipe. That is, first, you are going to start for a base manifold M as a Riemannian homogeneous space, J over H. And we want that this Riemannian homogeneous space, that is this quotient of two Lie groups, is scalar. That is, we want a complex structure, that is, we want a scalar form, which is compatible with the Riemannian geometry of the space. This scalar form will allow us to define a winding form on a suitable bundle. So this bundle is constructed as follows. That is, how do we generalize, the Stiefel fibration, the Hopf fibration, and so on. So we are going to pick a subgroup of H, and we can construct, using an old construction due to Bérat and Bergerie, a fibration of homogeneous spaces whose top space is G over K, and G over K can be seen as a bundle over G over H with fibers isometric to H over K. And the natural projection map from G over K to G over H is a Riemannian subversion with totally geodesic fibers. So from the connection form of this bundle, that is from bundles you have a connection form, the connection form of this bundle will induce on G over H a one form, which is R valued, if the space is scalar, on G over H, and this one form has a property that its exterior derivative is almost everywhere the scalar form of G over H, which is a scalar symmetric space you started with. So this one form alpha on G over H is a winding form. So this is a rather involved geometric construction, but it allows, for some explicit computations in the class of examples that I gave you. And then the good news is that you have an integrable functional that is, you are able to interpret alpha as a winding form and to interpret the integral of alpha along the Brownian motion x as an angular motion of something, that is, in the case of entire groups, as a determinant of a minor, but this integral has always a geometric interpretation. And the claim is that you get an integrable functional that is, his Laplace transform can be computed rather explicitly. So there is a setting in which computations are very nice. This is a setting of so-called generalized flag manifolds, which are a class of spaces generalizing this complex Grassmannian that I've been speaking about today. So I believe this is all what I wanted to tell you for today. So I thank you for your attention, and I welcome any question you will have related to the talk.
Okay, great. Thank you very much, Fabrice, for a very
Thank you.
interesting talk. Does anybody have any questions? I actually have a question, but it's bringing it back to sort of the case in the plane rather than sort of on more general
Yes, of
manifolds.
course.
If you look at rather than Brownian motion, rather than just taking one point out of the plane, but you take 2 points out, then I have seen that the Brownian motion sort of gets tangled around the 2 points.
Oh, yeah, exactly. Yeah.
Yeah, and it doesn't ever, it gets to a point where it never unwinds after that. It never untangles itself. Yeah. And I'm just wondering if there's any way, I haven't seen this anywhere, but have you seen any more sort of detailed analysis of this, let's say, where you kind of keep track of how tangled it is, maybe, or something like that?
That will be a very interesting research project, actually. That is, I believe that things can be done, you know, on the sphere to start with. That is, instead of looking at winding around 1 point, you look at winding around 2 points, or winding around a finite number of points. You know, in the case of the plane, indeed, as you say, there were some well-known results, and there are some explicit computations due to Pitman and Yor. This type of theorems, I plan to investigate them in the future, you know, in this geometric setting. For now, what I've been doing, this is to push, you know, the case of winding around 1 point in a large class of spaces. This took us some time, you know, to understand what is a class of spaces for which the computation work. But once we finish this project, indeed, that will be very interesting to look at the case of 2 points. Yeah, so that's a very good question. But for now, I don't know the answer to it. But I believe that some computations and some analysis might be done. Yeah,
Yeah, it would be great if some results.
Yeah, I think that would be interesting. Yeah.
Yeah. Okay, any other questions? All right, I guess that's it then. Thanks everyone for attending, and thanks once again to Fabrice for giving us such a nice talk.
Yeah, thank you very much for inviting me. And
hopefully you can come to Melbourne at some point.
Yeah, that would be great. So I hope to see you and some of you at a later date during a conference. Sometimes maybe SPA in Australia.
Yeah. Well, we hope it will be in a few years. We'll see.
That would be good. I would be very glad to come. Yeah.
Sure.
So thank you again for the invitation, and bye.